All right, my bad, y'all. Computer decided to restart right when class started. All right, so we're going to kind of pick up where we left off, talking about chemical reactions. We're going to introduce a concept called solutions. Solutions are a really important medium in which chemical reactions take place. I may mention I was a biochemist in my training. All biochemistry is solution-based chemistry. So literally every reaction I ever did was a reaction in solution. So solutions, really important in chemistry, okay? And that's going to be our topic of discussion today, solutions. All right, so strictly speaking, the definition of a solution is a homogeneous mixture. Okay, and to be clear, by homogeneous, we mean everything is evenly distributed throughout that mixture. So if you take a scoop on the top and you looked at it from an atom level, it would look the exact same as if you took a scoop from the bottom. Right? Everything is perfectly distributed. This is a fairly simple definition. Anything technically that's a evenly distributed mixture would be considered a solution. So air that we're breathing right now is considered to be a solution. It's a mixture of oxygen gas as well as nitrogen and a little argon. But strictly speaking, when we're talking in the lab, when we talk about solutions, 99.9% of the time, we're talking about liquid solutions, okay? So just an example here is if we take sodium chloride and we dissolve it in water, we would create salt water. And in my example here, the salt water is the solution, right? You take this salt, you dissolve it in another liquid, you create this even mixture. That would be a solution. You are going to do this exact same thing in lab today, right? You're going to make a solution with sodium chloride. All right, so then some other terminology here. In my example, the sodium chloride is what we would call the solute. And the water, the thing that I dissolve my solute in, is what we call the solvent. All right, so this terminology here, we can say a solute dissolves in a solvent to create a solution. All right, we're going to use these terms, solute and solvent, throughout the day. So importantly that we have a definition here. Right? Again, our solute is what we take and we dissolve it in our solvent to create our solution. Okay, cool. Generally speaking, what you'll be using in the lab for your solvent would be water, what we would call an aqueous solution. All right? That's not always the case. Actually, last week, if you think back, you made a solution with methanol and your iodine and zinc mixture. Right? So that was using a different solvent than water. But generally speaking, at least at this stage in your chemistry career, the solvent is water 99.9% of the time. Okay? Cool. All right, so we got some definitions down. Now we're going to look at solution composition. By that, I mean, what does this solution look like if we were to kind of like hop down in our magic school bus and shrink on down and look at it at the atomic level? All right, and this picture that we have in our heads is different for ionic compounds than it is for covalent compounds. All right, so we're going to look at these one at a time here. All right, I'm going to make a beaker. And I'm going to fill that beaker with my solvent. I'm going to use water. Cool. All right, and now I'm going to take an ionic compound. So for example, we like our go-to sodium chloride. Okay. I'm going to represent my sodium ions with an orange dot and my chloride ions with the green dot. Put a plus sign in for my cation sodium and a minus sign in for my anion chloride. Okay? And again, what we're going to see is what it would look like if we put our sodium chloride into our solution, into water. Just a reminder, I've pictured one formula unit there with our sodium ions and our chloride ions. Let's not forget we had this sort of picture of what sodium chloride looks like. It's this repeating array of positive and negative charges, right? Sodium ion, chloride ion, sodium ion, chloride ion, extending into infinity. So we're going to take this big old block of ions here, and we're going to dissolve it in water. We're going to put it into our beaker here and dissolve it. All right? And what we're going to see is that our ionic bond is broken when this solution is formed. Now I have just individual sodium ions floating around and individual chloride ions floating around. They are no longer bound to one another. They're floating around independently. All right? Our ionic compounds, we say, dissociate in solution. That word dissociate is a fancy way of saying break up into cations and anions. All right, so we actually break that ionic bond. So that we form our individual cations and anions. All right, so just like I have pictured here, now these things are floating around independent of one another in this solution. Okay, so what we can draw is what's called an ionic equation. This is a skill we're going to kind of like lay out here and then put to use next class as well. Okay. So my sodium chloride, when I make a solution with it, what should be my phase symbol, my state of matter that I put in my chemical equation here? AQ, right? That's what that AQ means, is we have an aqueous solution. All right, so you can represent this as sodium chloride put together with that AQ, all right? Or we can sort of illustrate this even more using this ionic equation to show that these will dissociate into sodium ions and chloride ions that are now separated from one another. All right, let's practice. Let's do another one here. Let's do MgBr2 AQ. Okay, notice that we need our charges for each ion here. So what should I use for my magnesium ion? +2 charge. All right, and then everybody real quick, let's notice how we do these bromides here, because how many bromines do we have in our formula for magnesium bromide? 2. So when this dissociates, it's going to dissociate into 2 bromide ions. All right, my 2 from my chemical formula is going to become that coefficient in my ionic equation here to indicate that I have 2 of those bromide ions. All right, so ionic compounds, when we take them and we dissolve them in solution, we're actually breaking that ionic bond, that opposites attract interaction between those 2 ions, and now they're all floating around separately from one another in our solution. Okay, this is different from covalent compounds. All right, I'm again going to make my beaker here. All right, but now what I'm going to add to this is a covalent compound. So let's take, for example, NH3 ammonia. You can make a solution with water and ammonia. All right, I'm going to picture my nitrogen atom as this dark blue dot, and my hydrogen atoms as black dots. All right, and I'm going to show that covalent bond between my nitrogen and my hydrogen. Boom, boom, boom. Cool. So that's what an ammonia molecule would look like here. Put an N in the middle. Cool. All right, so if we take this and we make a solution with our ammonia, unlike our ionic compounds, we have no bonds that are broken. All we have are just individual ammonia molecules floating around in this solution. Okay? So for our covalent compounds, we do not break our covalent bonds. Remember, these clusters of atoms that are covalently bound together we call molecules. So what we have when we create a solution with a covalent compound are just our molecules floating around independently. All right, so we got 2 different mental images about what happens when we create solutions. If we create a solution with a covalent compound, we're just taking those molecules and separating them, so now they're floating around independently of one another. With an ionic compound, though, we actually break that ionic bond between our cations and anions, and now these 2 individual ions are floating around separately. Cool? Cool. All right, so that's all well and good. We got to talk about solutions quantitatively, and we do so using what we call concentration. All right, so strictly speaking, concentration is simply the amount of a solute that you have in your solution, right? A measure of how much, for example, sodium chloride there is in this solution that we just prepared. There are a few different ways that you can measure concentration. Different fields find it more convenient to use one sort of set of units or another. In chemistry, we have one that's very specific to chemistry, and that is what's called molarity. Molarity, we use this uppercase M as our symbol for. All right, and the definition of molarity is moles of solute divided by liters of solution. Right? Moles per liter, you'll hear a lot, is the same as molarity. Strictly speaking, it's the moles of solute that are dissolved in your volume of solution, in liters of solution. Okay, cool. The reason why chemists like to use molarity is because chemists talk about chemical reactions in units of moles, right? That's what we were doing last week. We're saying, okay, if we start with this much product, or this much reactant, how much product are we going to generate? What did we have to do to use that balanced chemical equation was to convert to moles, right? So when in doubt, convert to moles. And that's why these units of molarity exist here, because again, chemists love moles. All right, so let's use this definition a whole bunch here. So first, let's say that we're going to prepare a solution. So solution preparation. All right, cool. Solution of, let's use that same ammonia example, is prepared by mixing 6.75 moles of NH3 into 1.6 liters of solution. And we can say we're mixing it with water. All right, so we want to use our definition of molarity here. Moles of solute over liters of solution. All right, what's my solute? The NH3. My solvent is that water. And I'm about to calculate the concentration of the solution that I prepared by taking that 6.75 moles of NH3. Whoops. Divided by 1.6 liters of that solution. All right, so I punch that into my calculator. I get 4.21875. All right, let's look carefully at our math here. What cancels out units-wise? Or is that a trick question? Yes, nothing cancels out, right? So I'm left with still my moles over liters. But again, that is our definition of that big M molarity. So we can, instead of saying moles over liters, write that big M. Okay. Do I have to worry about sig figs with the concentration? Yes, absolutely. This is a measured value here, so we're going to be limited in our sig figs by our input. We had 3 sig figs in our moles and 2 in our volume, so I'm going to round this off to 2 sig figs here. All right. So 4.2 capital M is our concentration here. Another way that we sort of represent this is this sort of bracket notation. Bracket NH3 is equal to 4.2 big M. The brackets specifically mean concentration of whatever it is in your brackets, in this case NH3, in molarity. So this sort of bracket notation here is code for concentration of in molarity. Cool. And so that's all well and good. If I've given you moles of solute, you can figure it out using the definition of molarity. But of course, there's no mole counting machine in this room. Instead, if we wanted to measure out a specific amount of ammonia, we would have to go over there to the balances, or what we're going to do this afternoon with sodium chloride. And then we would have to convert to moles. How do we get from grams to moles? Molar mass. All right, cool. So a way more practical problem would be the following. Everybody take a second and calculate the concentration of this solution. All right, we're going to make this solution with sodium chloride. We're going to take 26.3 grams of sodium chloride and create a solution with a total volume of 0.25 liters. Okay, so we convert from our grams of sodium chloride to moles of sodium chloride by dividing by that molar mass that we calculate from our periodic table. And we get 0.4500152. All right, and what are the units on that value? So we got moles of sodium chloride here. Am I going to round my moles of sodium chloride yet? No, because I'm not done with my math, right? So I'm just going to keep my sig fig marked, but I'm going to take that whole number to go on and do my molarity calculation using our definition of molarity. Plug in that value for moles, sodium chloride, my solute. Divide it by that 0.25 liters. And I get, we can use our fancy bracket notation, our concentration of sodium chloride is equal to 1.8000, whole bunch of zeros, moles per liter, which then I can round off to my 2 sig figs here. So 1.8 big M molarity. Cool. box around it. Boom. All right, so that's how we calculate molarity. Again, if this is a very practical example, something that you'll do here in lab today. We're going to make a solution by massing out a specific amount of sodium chloride, and then you can calculate the concentration of that solution by converting to moles and then dividing by the volume of solution prepared. All right, cool. So now, what about using that molarity in a problem here? So what do I mean by that?
Wait, what if it's a solution in milliliters? Do you have to convert it?
The definition of molarity is moles per liter. So yes, you would convert to liters first. Yep. All right, so now what if you're given a solution here? So for example, say how many moles of NaCl are in 0.63 liters of a 2.79 molar solution. So now I'm not asking you for the concentration, I'm giving you the concentration, and you're going to need to use it to figure out how many moles are in a given volume of your solution. All right, so the key here, it's going to be the exact same game that we've been playing over and over and over again with our units, but the key is we got to know how to turn this piece of information from our problem, that 2.79 big M, into something that we can actually use in our math, all right? And this is going to be a similar procedure for what we had to do to molar mass or what we had to do to density. We had to split up those mixed units, right? So we're going to do the same thing here. In order to use that 2.79 big M in our math, turn it into a conversion factor, we're going to split it up so that moles of our solute are on top and liters are on the bottom, right? Break those units back up to create our conversion factor here. Okay, so 2.79 molar, 2.79 big M, is the same thing as saying there's 2.79 moles of your solute in 1 liter of solution, right? Think back to how we did grams per mole. We split them up. Look back at our previous problem here. Split them up, grams, in this case, under moles. We're going to do the same game with our concentration here. All right, in this case, our moles are that NaCl, our solute. Okay, so then we just sort of set up our problem here with our 0.63 liters. Like any conversion factor, I can use it as is or flip it depending on what my unit setup is. In this case, I'm trying to cancel liters, so my liters will be on the bottom, and my moles of solute, NaCl, are on top. So I'm going to multiply that 0.63 by 2.79. Get 1.7577. All right, and if we look carefully at our units, my liters have canceled out, and so now I'm in moles of NaCl. And then the last step, sig figs. So I'm going to round this to 2 sig figs here because of my volume. So 1.8 moles of sodium chloride are in that 0.63 liters of that solution.
Is that conversion factor exact?
No. So both of these, I kind of hurried through the sig figs. Let me be clear. Both of these are measured values. My volume has 2 sig figs. My concentration is also a measured value. It just has 3 sig figs. So in this case, I'm limited by my volume. But no, molarity is definitely not exact. Definitely a measured value. Okay? And again, the key here is we're given this concentration in our problem, 2.79 molar. We need to be able to take that and turn it into something that we can use in our math by splitting up those units, right? That big M is moles per liter. We want to split them up into moles over liters. Oh, okay. I'm sorry. The 1 is exact. The measuredness is all in the top number. kind of like with our molar masses, over 1 mole, that mole is considered to be, that 1 is considered to be exact. You put all your uncertainty into that measured number on top. All right, cool. So then given this, you guys are gonna do one more example for me. All right. Let's say, what volume of a 6.43 molar solution contains a certain number of moles, 2.333 moles of KBr. All right, so I'm going to start out with my moles of my solute, my KBr. I've turned my concentration into a conversion factor that I can use in my math, and I'm going to have to divide by that conversion factor, divide by that molarity to convert from moles into liters. All right, my units of volume. So punch that into my calculator, 0.36, 283. And again, my units are in volume in liters. How many sig figs should I round this off to? Right, my number of moles has 4, but my molarity has 3. I gotta go with what's fewer, what's less. 0.363 liters of solution. That's how much I would need to get that 2.333 moles that I need in my chemical reaction, for example. All right? And so basically what we've done by introducing our molarity here is learn how to create another conversion factor, right? If we look here, we converted from moles into liters using that molarity. And in the previous problem, we did the exact opposite. We converted from liters to moles. Right? That's what our concentration is going to allow us to do, to convert from that unit that we need to talk about chemical reactions, moles, from a unit that's very convenient to measure in the lab, volume. All right, so that's what solutions are going to be used for, and you can maybe kind of see where this is going in terms of plugging it into our understanding of chemical reactions. All right, before we do that though, we're going to talk about another property of solutions, what's called solubility. Let's actually ignore all that. Okay, so solubility is the amount of a solute that will dissolve in a solution. All right, and at this point in our Chem 1A careers, we're going to divide the world of ionic compounds into two bins, right? This very black and white approach to looking at solubility. An ionic compound is either considered to be soluble, meaning it will dissolve in water, or it's considered to be insoluble, meaning it will not dissolve in water, all right? And so thus far, we're going to just classify the world in those black and white terms. An ionic compound is either soluble in water or insoluble, meaning it won't dissolve in water, all right? So let's lay down these two terms here. Again, soluble will dissolve in water. Insoluble will not dissolve in water. All right. And what we're going to do is we're going to be given a new addition to our constants page. I'll have them printed out for you next time to use. I forgot them in my office, to be honest. But yeah, so we got a new sort of addition to our constants page, as well as you can refresh your periodic table. I'll hand those out next time. But it's going to look something like this here, this chart. And what we want to do is we want to use this chart to be able to tell whether a compound is considered to be soluble or insoluble. All right. I'm going to break this into two parts here. So let's ignore the bottom half for right now. All right. So what we do, we're going to use sodium chloride here as our first example, and we want to determine whether it is soluble or insoluble. Now, first of all, I think we all know whether or not it's soluble or insoluble. Sodium chloride, table salt. Will it dissolve in water? Cool. All right, so let's make sure that this chart tells us that same thing here. All right, so what we're going to do is we're going to look up the anion in your compound. Sometimes you can find the cation, but not always, only in special cases here. All right, so generally speaking, we're going to try to find, and we'll do both for sodium chloride just to convince ourselves we get the same answer. All right. Everybody take a sec. Oh, and you're going to look up the anion on the left-hand side of the chart. So for our example, sodium chloride, everybody take a second and find where the chloride ion, or anion, is on this chart here. All right, we see it? Third box down. Boom, here's my chloride ion. So what this chart is telling me is that most chlorides are water-soluble compounds. All right? Any sort of generic chloride you pick off the shelf, chances are that it is a water-soluble compound, except when it's paired with these few insoluble exceptions over here. If it's paired with silver, mercury, or lead, it is an insoluble compound. Otherwise, it's soluble. All right, so sodium chloride, is that soluble or insoluble? Is it one of our silver, mercury, or lead insoluble exceptions? No, so then it is indeed soluble. All right, now we could even convince ourselves by looking up sodium, because sodium's special. You'll notice that sodium is listed as well as all the other group 1 metals here. The group 1 metals are kind of special in that it says that all these sodium compounds are soluble. And what are the exceptions? None, right? So without exception, sodium compounds are soluble. All right, cool. So take a second and use the chart and see if you can't classify these remaining three here as being soluble or insoluble based on the reading of our chart here. So I'm going to find my bromide ion right next to chlorine. It's got the same insoluble exceptions, silver, mercury, and lead. And magnesium is not on that list. So this is indeed soluble. What about barium sulfate? Soluble or insoluble? All right, cool. So if we look up that sulfate ion, my anion, SO4 2-, it says that most sulfates are soluble, but there are some exceptions, such as when it's paired with silver, mercury, lead, calcium, strontium, or barium. We got an insoluble exception here. So this is insoluble. If instead I pair that sulfate with magnesium, magnesium's not on my list of exceptions here, so that would make that soluble. Cool. All right. So now we're going to play the same game here, but we're going to introduce this bottom half. Okay. Let's just take, for example, magnesium carbonate. We're going to play the same game where we look up our anion on our table here. I see the carbonate ion right here. Okay, but this table is saying, the lower half here is saying the opposite of what the top half is saying. This is saying that most carbonate compounds are insoluble, and then there's a handful of exceptions that are soluble. All right, so then again, we're going to look here. Is magnesium one of our soluble exceptions? No. So that makes this compound insoluble. Right? Again, most carbonates are insoluble unless you're on this short list here. Magnesium was not on that short list, so it is an insoluble compound. All right, I'm going to put down two more, and you guys are going to tell me whether it's soluble or insoluble. All right, potassium phosphate and iron 2 hydroxide, soluble or insoluble? All right, potassium phosphate, what do we got? Soluble. We look up our anion, that phosphate anion. It says most phosphates are insoluble, but one of the exceptions is when it's paired with potassium. All right, and then iron 2 hydroxide. Again, I'm going to find my anion, that hydroxide ion. Is this one soluble or insoluble? Insoluble, because it is not on our list of soluble exceptions. Cool. All right, one other thing to point out. Again, this is going to be an addition to our constants page. One thing that's kind of nice about this addition to our constants page is now y'all don't have any excuse for not knowing your polyatomic ions, because we got a little bit of a cheat sheet here, right? We have nitrate ion, right? You got the name and the formula, so I shouldn't be able to stump you with these polyatomics anymore. Cool? All right. All right, so we're going to sort of put this particular concept of solubility more to the test next time. For now, we're sort of going to move into another property of solutions that we need to cover, what are called dilutions. All right, so our dilution formula that we got to know is M1 times V1 equals M2 times V2. All right, capital M's, which stand for which units? Molarity. All right. So this dilution formula here will allow you to calculate the concentration from a dilution. All right, and importantly, what do I mean by a dilution? This is when we take a more concentrated solution and mix in some more solvent so that it's less concentrated. All right, oftentimes when you go to clean, you take your cleaning product and you dilute it into some water to then go and clean your house with. You don't want to use the concentrated stuff, right? Same sort of idea here, but now we can calculate the concentration of our dilution. So again, a dilution is where you take a more concentrated solution mix in more solvent to create a less concentrated solution. All right, so we got this formula here. Let's define all these terms. M1. We said that M is molarity, right? So this is the concentration of what's called your stock solution. Okay, that word stock was used for your most concentrated solution. All right, so practically speaking, where does this come from here? Like when you work in a lab, you have like this bench and you got all your solutions that you've prepared on your bench top, right? So every 6 months you would go and you would create a whole bunch of new stock solutions. And then throughout the next 6 months, you would use those stock solutions by taking a little bit and diluting it to the amount that you needed when you did your experiment, right? So we keep these really concentrated bottles on our bench top and we prepare dilutions from those concentrated bottles when we need a particular chemical, all right? Cool, and again, this formula is gonna allow us to keep track of the concentration of our new solution here. The V stands for what? Volume. So that's the volume of our stock solution. Okay, but we're going to add this very important caveat. The volume to our stock solution that's used in your dilution. Right? If I'm in the lab and I'm taking a little bit of my stock solution to prepare for use in my experiment, it doesn't matter how much I have sitting on the shelf. What matters is the volume that I use in my dilution, right? Cool. M2, that's the molarity or the concentration of your dilute solution. And V2 is the total volume of that dilute solution that you've prepared. right? So this formula here will allow us to keep track of our concentrations as we're performing a dilution. All right, one more thing that we can note about this formula that's just kind of helpful to keep in mind, and we'll see this when we do our example here, but your units of volume do not matter as long as they match. You could do it in liters, you could do it in milliliters, you could do it in kiloliters or centiliters. It doesn't matter as long as your volumes match in that equation. Okay, it's actually true of your concentration units as well, but we only know the one for right now. All right, so let's put this M1V1 equals M2V2 to use here. Let's do an example. What is the concentration of a dilution 2.5 mLs of 6.44 molar NaCl is diluted to 460 milliliters. In our equation, M1V1 equals M2V2, what are we missing? What are we trying to solve for here? M2. All right, I have my concentration of my stock solution, that's 6.44 molar. I have the volume that I use in my dilution, and I have my total volume of that dilute solution. All right, so the only thing I'm missing is M2. So I'm going to divide both sides by V2 and then plug everything in and solve. Okay, so my 6.44 molar times that 2.5 ml, that's how much is used in my dilution, divided by the 460 mils. Okay. My M2 is 0.035. That's what the calculator spits out. What are my units here? Big M, right? And let's just convince ourselves looking at our math here. We have our concentration in molarity times our volume. Notice I didn't have to convert my volume to liters. You could, it was just be an extra step, because my volumes will cancel out their units, leaving me in units of just concentration, right? My big M molarity. And then in this case, the calculator did a good job with sig figs here, got lucky. I should have 2 sig figs in my final answer. Cool. All right. We're going to be performing a dilution here today. So we're going to be using both of these calculations in practice here today in lab. We're going to be both massing out a certain amount of sodium chloride and calculating the molarity of that solution. And then we're going to take that stock solution and do a bunch of dilutions using this formula here to figure out what the concentration is of those dilutions. Okay. Now I want to sort of tie this back into what we learned last week and talking about solution stoichiometry. Many types of solutions occur, many types of chemical reactions occur in solution. There is one particular type that we're just going to beat to death here in this class, what are called precipitation reactions. All right, your precipitation reactions are when you mix two solutions and you form a solid product. All right, so let me just give you an example. We'll talk about how we predict these products and all that jazz next class. But just to look at an example of a precipitation reaction, we're going to take our favorite example, sodium chloride. But again, it's going to be an aqueous solution of sodium chloride. All right, and we're going to mix that with silver nitrate, which is also aqueous. Right, so I'm mixing these two solutions together. This is going to be a double displacement reaction, so I'm going to swap the sodium and the silver. So now I'm going to pair the sodium with the nitrate and the silver with the chloride. All right, but again, now let's look at the states of matter of these products here. This sodium nitrate is actually still aqueous, but importantly, I've formed this solid silver chloride in this reaction. All right, so again, we have to form a solid product in a precipitation reaction. That's in this case, my silver chloride. All right. So how did I know that? We'll get to that next class period. For right now, you're just going to trust me. Okay, but importantly, a precipitation reaction is when we take two solutions, so two aqueous solutions, we mix them together, and we form that solid product. Cool? All right. So now we have this reaction. Now let's do some stoichiometry with it, some quantitative stoichiometry here. We're going to say if 0.45 liters of 2.95 molar NaCl is consumed, how many grams of that silver chloride are formed? Okay, all right, let's think about this for a second. Now, granted, I have stoichiometry written at the top of the page, so that might have been in and of itself a good hint as to what we're going to need to use. But even if I didn't have stoichiometry written at the top of the page, anytime we're talking about the math of a chemical reaction, in this case, I'm starting with a certain amount of sodium chloride, and I'm trying to figure out how many grams of silver chloride are produced. I need to jump from this quantity to this quantity in our chemical reaction, I know I'm going to need to use a stoichiometric ratio. All right, that's how we do math with chemical reactions. So I know somewhere in my math, I'm going to have my stoichiometric ratio 1 mole of NaCl to 1 mole AgCl. All right, anytime we're doing math with our chemical reactions, we're going to need a stoichiometric ratio. All right, I might have to flip it upside down depending on what my units are, but I know I'm going to have to use this conversion factor here. Now, what I'm given is a volume and a concentration. I have liters, and then I have molarity of that sodium chloride. Can you use those values to get to moles of sodium chloride? Great. Then you can just plug it into our regular stoichiometry. All right, so everybody take a few minutes based on the example that we did previously using our molarity. See if you can't calculate moles of sodium chloride, and then you can use our conversion factor, our stoichiometric ratio here, to jump from moles sodium chloride to moles of silver chloride in your math. All right, so I'm going to take my volume and multiply it by that concentration because I split it up into moles over liters. So I could see that by setting it up that way, my liters cancel. Then I'm going to use my stoichiometric ratio to jump from moles sodium chloride to moles of silver chloride. And then lastly, it wants the mass of product. So I'm going to use my molar mass to get from moles to grams. So punch that into my calculator, 190.25849. All right, my units are my grams of my product, my silver chloride. And then how many sig figs? Just 2. So 190 with no decimal place grams of that silver chloride product are going to be produced in this reaction. Okay? All right, and what we can see is from a unit perspective here, we converted from our volume into moles. Again, using that new unit, the molarity. We then converted from moles of sodium chloride to moles of silver chloride using what we learned how to do last week, our stoichiometric ratio. And then finally from moles of silver chloride into grams of silver chloride using our molar mass. Cool. Fun stuff. All right, we'll learn more about these precipitation reactions next class period. For now, I'm going to take a minute